All right, what is up, everyone? We're moving into lesson 2 of our introduction to probability. The lesson before, we talked about simple probability. We also talked about compound probability with independent events. Today, we're going to move on to dependent events, and we're going to get into mutually exclusive and inclusive events on the other side. But we're going to start off with dependent events to get started. All right. So example 1 says the Latin Club is holding a raffle at a football game with 2 prizes. After the first ticket is pulled out and the winner determined, the ticket is taped to the prize. The next ticket is pulled out to determine the winner of the second prize. Are the 2 events independent? Spoiler alert, they are not independent. They are going to be dependent events. And let's talk about why they're dependent events. Well, think about there's 100 people at this football game, and each of those 100 people buy a ticket to win these 2 prizes. Well, they pull a ticket out of that 100 and they stick it to the prize. Now there are only 99 tickets in the drum or whatever they have the raffle tickets in, so the next chance of winning is 1 out of 99. So the very first probability is 1 out of 100. The second probability would be 1 out of 99. So that second ticket is dependent on what happens on that first ticket. It decreases the overall number of tickets that are in there. Now compare this to rolling a die. If I roll a 2 on a die, and then I roll another 2, or another die after that, the 2's not missing. I could still roll another 2. In this event, with the Latin Club raffle ticket, I can't pull that ticket out again. Once I pull a ticket out, it's gone. It's no longer part of our probability. So that's the difference between a dependent and independent. Independent, each event is not dependent on it. Well, that's a terrible use of word because that's what we're talking about, dependent. But that first, whatever event does not affect the second event at all. For a dependent event, the first event does affect the second event. So let's move down to some explanation. So we already talked about the probability of independent events yesterday, and that's what I'm looking at right now. And that is the outcome of the first event does not affect the outcome of the second event. And then we had kind of this equation here. Just kind of a reminder, or maybe this is the first time you've seen this. If you ever see an upside down U in math, that actually equals an AND statement. A right side up U, on the other hand, stands for OR. So this is read probability of A and B happening. Well, we said that the probability yesterday was just the probability of event A times the probability of event B happening, and that would be our total. If we had a C in there, we'd just multiply by the probability of C. So my example is rolling a 6 on a die and then a 5 on a die. Well, that would just be 1 over 6 times 1 over 6, which would equal 1 over 36. And I think we're going to actually do that down here in just a second. The second one we're talking about is probability of a dependent event. A dependent event says the outcome of the first event does affect the outcome of the second event. When calculating this, we have to account for the fact that the first event did affect the second event. So if we look at this equation, it says the probability of A and B happening is the probability of A times the probability of B following A. So when I talked about pulling the tickets at the football game, I said the probability of the first one would be 1 out of 100. Then the second one would be 1 out of 99 because we pulled that ticket out. It is now missing. So I'm going to note here that this one usually has a smaller number of outcomes. Usually. Because you're removing something. It's changing the overall number of something in a bin, apples in a basket, cards on a deck. However you have it, we're going to probably have a smaller number and that second one. An example would be without replacing the first card, choosing an ace, and then choosing a king from a deck of cards. We're going to talk a little more about cards on the next slide, but just so you know, there are 52 cards in a deck. So if I'm pulling out an ace, there are 4 aces. We would have a 4 out of 52 chance of pulling an ace. However, after I pull out an ace, and I'm looking for the king, we no longer have 52 cards in there because I pulled out an ace. So we now have 51 cards in there. So the second one would be out of 51. So our second event is affected by our first event. All right, let's start off with an independent event. So it says find the probability that you will roll a 6 and then a 5 when you roll a die twice. This has to be independent. This has to be independent because if I roll a 5 or a 6, that 6 doesn't disappear in the die and I can't roll it again. Instead, the probability of rolling a 5 stays the same at 1 over 6. It's not affected by me rolling a 6. So to calculate an independent event, it's just the probability of maybe a 6 happening and a 5 happening would equal the probability of 6 times the probability of rolling a 5. Probability of rolling a 6 is 1 out of 6 chance, times probability of rolling a 5 is a 1 out of 6 chance, which would equal 1 out of 36 chance that I roll a 6 and then a 5. All right, our next one is going to be a dependent event, and I'll show you the key word that lets me kind of know it's dependent. It's not always there, but if you see this string of words, you're probably going to have a dependent event. So a bag contains 3 marbles, 2 green marbles, 4 blue marbles. If 2 marbles are drawn randomly from a bag and not replaced. Not replaced generally means that it's going to be a dependent event. So let's think about this. I'm pulling out 2 marbles. So I reach in the bag, I pull out a marble, I set it off to the side. I grab another marble, I set it off to the side. So when I grab that first marble and set it off to the side, there's no longer the same number of marbles in the bag because I pulled one out. We're supposed to find the probability both marbles are blue. So this is going to be dependent. It is dependent. So what we're looking at is basically the probability of pulling a blue and then probability of pulling a blue on the second pull. Well, that's going to equal the probability of pulling out a blue. That one's not affected by the fact that it's dependent, but the next one will be. So we'll multiply that by the probability of pulling a blue, knowing that with 1 blue marble missing, because I already pulled it out. All right, so now we just have to calculate our probabilities. You'll notice on a lot of my answer keys, I might have like numbers circled and stuff, so I might do something like this. 3, 2, 4, and that's to keep it straight to my head that, okay, 3 plus 2 is 5, plus 4 is, there are 9 total marbles. So I know what I start off with. All right, when calculating this, probability of pulling a blue, there are 4 blue marbles in a bag with 9 marbles. First one should be easy. The next one is the slightly harder part of it. Now I have to go, okay, there's no longer a blue marble in there. So there's only 3 blue marbles left in the bag. There's also only 8 marbles in that bag because once I pull out a blue marble, it's a marble, so we have 1 less marble in there as well. Now I can do my multiplication. That's going to be 12 over 72, which reduces down to 1 over 6. All right, next one says a school survey found that 7 out of 30 students walk to school. Let me bring this up. On yours, it should say 3, so I'm going to change mine. If 3 students are selected at random without replacement, what is the probability that all 3 walk to school? So we have 30 students here, 7 of them walk. I'm going to randomly pick out 3 of those students. What's the probability that all 3 of them walk to school? Well, this is going to be a dependent event. It is dependent. And one of the signs I know is dependent is we kind of have this without replacement once again. And that means I grab a student and I pull them out of the bunch. And I say, do you walk or do you not walk? Then I send them off to the side. I grab another student. I say, do you walk or do you not walk? And then I set that person off to the side as well. So each person I pick gets removed from the group. So we're going to see that 30 students whittle down to 29 and then 28 students as I pick those students. So it is dependent. So the probability of someone walking and pulling someone else that walks and pulling something else that walks is going to equal the probability that that person walks times the probability that the next person walks as well. But we have to remember that we're missing a person. So it'd be a person that walks minus one walker. We'll multiply that by the probability of me getting another person that walks, but remember, we're missing another walker because he's pulled off to the side and no longer part of the group. All right, the probability that I pull someone that walks are that first batch of students. So we have 30 total students and only 7 of them walk. So the probability is 7 walkers out of 30 total students. Well, like I said, I take that person that walks and I set them off to the side. So there's only 6 people that walk now out of 29 students. Now that person is set off to the side as well. So now we're down to 5 people that walk out of 28 total students. Now we go ahead and do our multiplication. Remember, we multiply our numerators. 5 times 6 times 7 is going to be 210. And then our 30 times 29 times 28 is going to be 24,360, which simplifies down to 1 out of 116. All right, that is dependent and independent events all happening in similar problems. So on your homework, you have to decide whether it's independent or dependent before you move forward, because it does change the problem just a little bit. All right, our next thing we're going to talk about is mutually exclusive and inclusive events. So events that can occur at the same time are called mutually exclusive. That cannot occur. So events that cannot occur are called mutually exclusive. So my example down here is actually rolling a 2 or a 3. You cannot roll a 2 and a 3 at the exact same time on the same die. So it's either a 2 or it's 3. It's known as being mutually exclusive. Now, when we move into inclusive is if 2 events are not mutually exclusive. So they're not mutually exclusive. In other words, they can occur at the same time. So inclusive means that those 2 events can occur at the exact same time in the exact same event. My example down here is a king or a heart. Now, just a quick cards review. Every single card, so king is a card with K's on it. Our king has 4 different suits. You can have a king of spades, a king of hearts, a king of diamonds, and a king of clubs. So there are 4 different suits for our king. So when I'm asking for a king or a heart, there is overlap because this can occur at the exact same time, and that is a king of hearts. It matches both situations. Now remember, when I talked about the 2 or 3, it can only be a 2 or a 3. They can never occur at the same time. So a 2 or 3 cannot occur at the same time. Another example of an inclusive event, something that has overlap, would be maybe I have a whole bunch of fruits and vegetables in a basket, and I ask what's the probability of pulling out an apple or a red item. Well, an apple can be red, so there could be overlap. We could have a red apple, so it meets both criteria. So if there's something that can meet both requirements, that is an inclusive event. All right, let's talk about how we're going to calculate these 2 things. So where dependent and independent, which we talked about back here, were multiplication, and these were and statements. When we're doing these mutually exclusive and inclusive events, we're going to use or statements. So what's the probability of A or B? Or tells you are going to add instead of multiply. So we're going to add those 2 events together. So that is if I'm asking or. Now, if it's mutually exclusive, in other words, those 2 events are completely separated, we just do the probability of first thing happening plus the probability of the second thing happening. If they are inclusive, that means there's some overlap. And what you're going to do is you're going to add the probability of the first thing happening plus the probability of the second thing happening, and you're going to subtract out the overlap, because what you don't want to do is you don't want to count something twice. So if you think about this, kings or hearts, there are 4 kings and there are 13 hearts in a deck. So if I counted that up, if I counted 4 kings and I added 13 hearts to that, we would have 17 kings or hearts. However, there's a king of hearts that just got counted twice. It got counted in the kings column, it got counted in the hearts column. So we need to subtract 1 away so I didn't count the kings of hearts twice, since you're counting it in both categories. Let's see an example of this. All right, a card is drawn from a standard deck of playing cards. Find the probability of drawing a king or a queen. Now, the first thing you have to ask yourself, is it exclusive or is it inclusive? Well, to be exclusive, it means it can either be a king or a queen. To be inclusive, there must be some overlap. Now, there's no such thing as a king-queen card. It's either a king or a queen. There is no overlap, so this would be exclusive. It's either a king or a queen. So that means what we're trying to do is we're trying to find the probability of a king. Don't go back. Or a queen, which is just going to equal the probability of it being a king plus the probability of it being a queen. Well, the probability of it being a king, remember there's 4 kings in a deck of 52. There's also 4 queens in a deck of 52. Now note this is an or statement, so we don't have to worry about removing something and leaving it off to the side. This is an or, not an and statement. It's just one pull of a card. It is a single event. You are pulling a card. What's the probability of it being a king or a queen? So you add those 2 things together and you have 8 out of 52, which makes sense. If I have 4 kings and 4 queens, we have 8 cards that are successful in that deck. So that means we have an 8 out of 52 chance of being successful, which could reduce down to 2 over 13. All right, so I think that's a good thing to point out in these. These are single event items, probabilities. It's just one thing happening. We're just saying, what if it's 2 categories? All right, find the probability of drawing a king or a spade. Well, this is going to be inclusive because there is overlap. And that is because there is a king of spades. That card is in both categories. So what's the probability of pulling a king or a spade is going to equal the probability of pulling a king plus the probability of pulling a spade minus the overlap. What's the probability of pulling a king of spades? I should probably change these a little bit. But anyway. All right, so that's going to equal probability of pulling a king is 4 out of 52 cards. There are 13 spades in a deck. Now, like I said, if I just added these 2 things up, I'm counting the king of spades twice. Because there's a king of spades in here, and there's a king of spades in that 13. So we need to subtract out. Because we counted it twice, we need to subtract it out. So we're going to subtract out 1 king of spades, which is going to equal our 16 out of 52, which is going to reduce down to 4 over 13. All right, that's how you tackle if it's exclusive or inclusive. So what we need to do in these upcoming problems is decide, is it inclusive, is it exclusive, and then use that information. So our first one says, in a group of students, 60% are commuters, 50% are female and 30% are female commuters. So in a group of students, 60% are commuters, 50% of those students are female, and 30% are female commuters. Find the probability that a randomly selected student is either female or a commuter. So we're trying to do the probability of whether it's a female or it's a commuter. So what you're going to ask yourself, is there overlap? Is there such thing as a female commuter? Well, it says it right in the problem that there's 30% are female commuters. So there is an overlap. So this is going to be inclusive. There is overlap. There's such a thing as a female commuter. Both things fit the category. So that means what we're going to do is we're going to find, okay, we have a group of students. So there's men in it, there's people that are commuters, there's people that are not commuters. We just don't talk about how many guys there were. So what we're going to do is we're going to find the probability that the person I randomly select is female. I'm going to add the probability that it's a commuter because it is an or statement. But there are some female commuters, so I need to subtract, so I don't double count them, the probability that it's both. Because if I count up all the females and I count up all the commuters, I actually counted some people twice. Because if you're a female commuter, I counted you in the female group and I also counted you in the commuter group. All right, let's move forward. So the probability that it's a female to start off with, well, they said 50% of the people in this group were female. So we're going to have 50%. Plus, how many people are commuters? Well, it says 60% of people are commuters in this group. Now, I want you to look at that. If I just did 50 plus 60, I'd have 110% of people are female or commuters. That doesn't make any sense. Once again, I counted female commuters twice, so I need to subtract one of those groups out. So I'm going to subtract the overlap, which is 30% of people are females and commuters, which is going to equal 80%. That is a perfectly good answer, 80%. However, you can throw these into fractions if you wanted to. You could change 50% to 50 over 100. Plus 60 would be 60 over 100. Minus 30 over 100 would equal 80 out of 100. Which would equal 4 over 5. Both of these are valid answers. Also, you could have turned it into decimals. So you could have did 0.5 plus 0.6 minus 0.3, and that would have given you 0.8. 0.8 would also be a good answer. All right, last one. Ooh, I have it right here. All right, when a pair of dice are rolled, find the probability of observing a sum of 12 or at least one die showing a 2. Now, these are really, really tricky problems because these can be inclusive or exclusive depending on what numbers we're talking about. So what I want to note is I need to figure out, how do I get a sum of 12? Well, I get a sum of 12 by rolling a 6 and a 6. Now let's circle all the ones that have a 2 in it. All of those have a 2 in it. All of these have a 2 in it. Is there any overlap between a sum of 12 and having a 2 in it? No, there is no overlap. Now, I want to show you one that would have overlap really, really quick, and then we'll go back to this. If I would change that to not being 12, let's say I change it to a sum of 8. If I changed this to a sum of 8, don't do it, just pay attention. If I change this to a sum of 8, I would then have 2, 6, 3, 5, 4, 4, 5, 3, and 6, 2. These would be inclusive. There are 2 cases where there's overlap, where there's a 2 in it and it adds up to 8. So be careful on problems like this because they can be sneakily either one of these exclusive or inclusive. In this case, it is going to be exclusive because 6 and 6 is the only way to make 12 and there's no 2 in it. So we have an exclusive event. It makes our life a little easier. So we just have to do the probability that the sum is 12 plus the probability that one die is a 2. All right, the probability of getting a 12, there's only one of those on that board, so that's 1 out of 36. Plus, here's kind of a really good representation on why, if you have an inclusive event, that you can sometimes double count something. So when I'm counting all the ones with 2s, I could go 1, 2, 3, 4, 5, 6. And then if I count down, we'd have 7, 8, 9, 10, 11, 12. But we're going to notice I double counted the one in the vertical row. That is where we actually subtract stuff from it. So we'd actually have 11 of these because we have 7. I'd have to skip this one, 8, 9, 10, 11. That's an example of double counting something. And that's what happens when we have those inclusive ones. We double count it and then we subtract it, just like we would do here. I think most of us would have counted those 6 and then came down and been, oh, don't count that one again. So we have 11 of those out of 36, which is going to equal 12 out of 36, which just equals a 1/3 chance of it either being a sum of 12 or have a 2 in it. All right, that is mutually exclusive and inclusive. We also covered our independent and dependent probability. Yeah, I think that's going to be good. I'm just checking out the homework real quick if there's anything I want to go over. I think everything's good. When you check my answer guide, you're going to see I write how many items there are every single time off to the side because you don't want to get that number mixed up. All right, everyone, good luck on the homework. Get it done. I will talk to you soon.